what I want to do right now is to finish up where we left off last time, which was, so we talked about this program called LCS, right? Longest common substring, right? And the goal is that, we have, for example, these two strings, X and Y over here, right? And then we're trying to find a bunch of letters that, or a sequence of, not a sequence, a subsequence of letters which occurs in both X and Y. Okay, so for example, this BCBA here, right? And we saw that we can do this in quadratic time, right? We can do this in m times n time, where m and n are the lengths of X and Y, right? And you can do that just by making this table over here and then filling out this table, okay? And you can also do that in quadratic space, right? And the problem is that if you do it in quadratic space, then even for moderate values of m and n, right? Like for m equals 1,000,000 or n equals 1,000,000, this is going to be too much space. And so now we're looking at some algorithm which can do this in linear space, right? M plus n space, okay? And the way that we're going to do this is that our observation is that if you look at the LCS, right, then this corresponds to a path in this matrix, right? So this gray path over here, right? And the path has this property that it starts out in the upper left corner, right, which is like the beginning of X and Y. And then it has to end at the lower right corner, which is the end of X and Y, right? And in addition, it always has to move either to the right or downwards, right? Either straight downwards or diagonally downwards, right? Like it cannot move upwards or to the left or anything, right? So the path is strictly going from the upper left corner to the lower right corner. Okay, and so that means that this path is going to cross the middle part of this matrix in some location, right? Which is the this red location I marked over here. Okay, and so now the basic idea for this linear space algorithm is that we're gonna find this entire gray path, but we're gonna do it step by step. Okay, so the first step is to just find this red location in the middle. Okay, so that's just one part of the path, right? And then after you do that, that's gonna subdivide the problem into basically the left half over here, right? And then the right half over here, okay? And then we're going to recursively solve those subproblems, okay? Meaning that in the left half, for example, we're again going to chop things down the middle, and we're going to find where this gray path crosses, okay? For example, this location I circled, okay? And then the same in the right path, right? And so here there are actually going to be two crossings like this, okay? All right, so then once we find these additional crossings, that's again going to subdivide the problem into another left half and another right half. And then again, we're going to find the crossing points, right, for each of these subproblems. Okay, so if we just keep doing this, then eventually you see that we're going to find all of these crossing points. And if you take all the crossing points together, that's exactly your shortest path, right, your LCS path. Okay, so that's the basic idea. So what we need to do is to have some way to solve each of these problems, right? Meaning that given a big matrix like this, if we chop it down the middle, we have to know where the path is going to cross this middle column over here. Okay, so we're going to call that we're going to call the crossing point. We're going to call that row J. Okay, so yeah, so the way this is going to work is that we need to observe something. It's basically the optimal substructure property. Okay, so sorry, yeah, okay, right. So oops, what is this? All right, sorry. All right, so the property is that if you take this path and then you take this middle crossing point over here, okay, then this is going to break the entire matrix into these two submatrices, the green one and then the red one on the on the lower part. Okay, and now you see that part of this path is going to go through the green matrix and the other part goes through the red matrix. And now the key property is that each of these paths also has to be an LCS path for a substring of X and Y. Okay, so what I mean by that is, for example, if you look at this green path over here, okay, right? So this is actually going to be an LCS for these two substrings of X and Y, right? Like once we chop down the middle, okay, then we're only going to keep half of Y, right? The first half of Y, okay? And then for X, yeah, so we have this part of X, okay? And you see that this path corresponds to an LCS of this part of x and y, right? The LCS being B and C. Okay, all right. And the same thing happens in the red matrix. Okay, so in the red matrix, what we have is that this path over here, this red path, okay, is going to correspond to an LCS of this substring of x and y. Okay, right, the CBA part. Okay, and yeah, so what that means is that if we can find this central location J, okay, then we can split the overall problem into two parts, and then now we can solve each part recursively. Okay. Yeah, so basically, I wrote that out over here. The first part, which is this green part, is an LCS for the string x going from the first letter to the jth letter, right? The j here is 3, okay? So it's for the first 3 letters of x, and also for the first 3 letters of y, okay? And the second part is an LCS for if you start at the 3rd letter, right? And then you go up to the middle part. Okay. All right. Now, there's something which is a little bit confusing over here, which is that you see in the second part here, what I'm saying is that we're going to look at the string y. Okay, we're going to look at this substring. Okay, but we're not going to look at it in the order C A B B A. Okay. Instead, we're going to look at it in reverse order. Okay, A B A C. Okay, and likewise for this substring of x, we're not going to look at it in the normal order C, B, D, A, B. We're going to look at it in the reverse order, okay, B, A, D, B, C. Okay, all right. And the reason we're going to do that, okay, is because we don't know what this row J over here is, right? Like here, we can see in the example that it's going to be 3, okay? But when you run the algorithm, initially you don't know what J is, okay? Yeah, so right, so that's why we're going to look at the second half of this problem. Okay, we're going to look at the reverse strings. Okay, in the first half, we're still going to look at things in the normal order. Okay, so that's kind of a preview of the algorithm. Now let me give you the full algorithm. Okay, so what we're going to do is we need to the first thing we're going to do is to find this location J. Okay, so let's see, did I write that here? No. Okay, so what should J be? Okay, so what we want J to be is we want to find some location along this column which can such that if you divide the problem there, right? If you divide it here, okay, then in the first part we see that we get two matches, right? Because the value here is 2, okay, and then in the part after J you get 2 more matches. Okay, so we want to find how many matches we can get in the first part and how many matches we can get. Let me switch to a different color here. Right, so fine, let me switch to purple. Okay, yeah. All right, so we want to see how many matches we can get in the first part and then how many matches we can get in the second part. Okay. And then we want to pick a J such that if you add up the total matches from the first part and the second part, this is as large as possible. Okay, because the sum of the number of matches from the first part and the second part is equal to the total number of matches that you get. Right? In this case, we have 4 matches. Okay, so what I'm saying is that if we instead of dividing over here, let's say that we divided over here, okay, then the path might be something like this. Okay, so now we're going to find how many matches we get in this part, right, which is like 0 matches, right, versus how many matches we get in this part, which let's say is like 3 matches. Okay, so then that gives us a total of only 3 matches. Okay, whereas if you split the things over here, right, you see that you get 2 matches in the first part and 2 matches in the second part, and that gives you 4 matches overall. Okay, yeah, so we're going to look at all of these locations, and we're going to see, if you subdivide the path there, right, if you subdivide over here, okay, how many matches do you get? Okay, if you subdivide over here, how many matches? Okay, we're going to try all of these locations and then see which one of those gives us the maximum number of total matches. Okay, and that's going to be the one that gives the LCS. Okay, so that's why J here has is going to be defined in this way. Okay, here this P value is going to be the number of matches in the let's see, in the first half. Okay, in like the left half over here. Okay, and then Q is going to be the number of matches in the second half. Okay, more precisely, let me switch back to red over here. All right, oops. All right, sorry, just 1 second. Okay, good. All right, yeah, so more precisely, you know, this P is defined in this way, okay? This P is defined as if you take all of the letters of X, okay? So here X is from 1 to M, okay? And then you take only the first half of Y, okay? So you only take the first half of Y, okay? So we're basically considering, isn't that going to count the common character? Yeah, so we need to be careful about that, right? So yeah, there's this common character in this middle row here, so we need to sort of do some corner case to take care of that. Yeah, that's true. Okay, but I'm just going to give like sort of yeah, we need to sort of remove that common character. You basically need to see if you get a match on the jth location. Okay, like here you do get a match, but then if you cut over here, right, the A and the C are not equal, so you don't get a match. Okay, so you either need to subtract out a common match in this middle column here, or you can just leave it there. Okay, if you get a match, as in this case. Okay, yeah, okay, so going back to this definition of P over here, right? So what we are saying is that we're going to take all the letters of X and the first half of Y. Okay. And then now we're going to take this matrix and you're going to compute all of the LCS values in here. Okay, so remember that we talked about this earlier, which is that you can compute all of these values in linear space because you only need to keep track of 2 columns at a time. Okay, yeah, so, oops. Okay, yeah, so that allows us to compute all of the values on the final column over here. Okay, so that's P, and then for Q, we're gonna look at these strings in the backwards order, right? So we're gonna take let's see, we're gonna take all of X again, okay, but now we're gonna go in the backwards direction, which is why I write this as XM to 1, okay, instead of M 1 to M. Okay. And then for Y, you're also going to look at things backwards. And again, you're going to compute all of the LCS values in here. Okay. Now, notice that whether you look at X in the forwards direction, right, in this direction, right, or the backwards direction, right? So as long as you look at both X and Y, both in the forward direction, or both in the backwards direction, okay, then when you compute the values in here, you're going to get the same matrix. Okay, yeah. Okay, so then we're going to define Q this way, right? So then Q is going to have all of the values in here. And now we're going to pick J so that if you add up the P value and the Q value, right, you get the maximum, you get the largest amount. Okay, and that largest amount will just correspond to the crossing point, which gets you the largest match, total match from the first half and the second half combined. Okay, yeah, so that's how we're going to find the J. Does that make sense? Any questions? Okay, yeah, you can keep typing into the chat box if you have any questions. Okay, all right, now, as we said, computing all the values is going to take quadratic time here and then linear space. Okay, yeah, and then now once you find the J, right, this middle part over here, right, now we've got 2 subproblems, this part and the part on the right. Okay, and so we're going to solve those parts recursively. Okay, however, we're going to solve the left part first, right, and then we're going to solve the right part. Okay, and when you do that, you can actually reuse your space. Okay, so for example, let's say that if you solve the left part, it takes you like you know, let's say 1 megabyte of memory or something, okay? But then after you solve the right part, you obtain this green path, okay? And now you can just reuse that 1 megabyte of memory to solve the right part. Okay, and then in that right part, you would compute the red path, right? And then you add them together. Okay, so basically, even though you solved 2 problems, each of which took 1 megabyte of space, right? But in total, you only use 1 megabyte of space, because after you were done with the first part, you reuse that 1 megabyte for the second part. Okay, so this is a key point here. This is something that's special about space versus time. Okay, when you do a computation, you can reuse space for several computations. Okay, but you cannot reuse time, right? Because if you have several computations, if each one takes like 10 seconds, then you can't reuse those 10 seconds, right? You don't get those 10 seconds back. Okay, but if each of them takes 1 megabyte, you can keep reusing that 1 megabyte multiple times. Okay, so this is why in the end the time is still going to be quadratic, right? But the space is going to end up being linear. Okay. Okay. So so that's the entire algorithm. Okay. So let me just go over that again, right? So what we're going to do is we're first of all going to compute all of these p-values. Okay. So the p-values are defined as the LCS values for this string x and the first half of y. Okay. And then that's going to take you linear time and linear space. Quadratic time and linear space. Okay. Next, you're going to compute all of these q values, okay, which is defined as the LCS values for this reverse string x and the reverse of the second half of y. Okay. Right. And then next, you're going to find this j value, which is that you're going to take all of these p values and all of these q values, and you look at which index here gets you the largest sum. Okay, so that's j. Okay, and after that, you break the problem into these 2 subproblems. Okay, the left half and the right half, and you go ahead and solve those recursively. And after you solve those recursively, what those recursive calls return are these paths over here. Okay, and then you just add that to your middle crossing point, and then now you have your entire path. Okay, so that is the algorithm. Okay, so I see there's a question here. Now that we just use 2 columns, why the space complexity isn't order n? Okay, let's see. Okay, order. Yeah, it's because in the I guess you can say it that way. Yeah, I'm not sure. I guess you can say it's order n complexity. Is that right? Yeah, I think it depends on like how you divide. So we should divide so like if y is longer than x, we should divide y in half, right? And so basically m and n are like the same order as each other. Okay, like order. Yeah. Let me sort of think about that a little bit more, and then I'll get back to you about that. Okay. Yeah. But the point is that order n and order m plus n are like the same asymptotically. Okay. That's right. Yeah. Right. M plus n is like the bigger of m and n. Okay. Okay. Any questions about how this algorithm works? Okay, again, you compute these values, you find the j, and then you go recursively compute the paths in both halves. And then you just piece everything together. Okay, right. So the final part is to show that this actually achieves this linear space complexity. Okay, and so what we're gonna do is let's see. Oh, wait a minute. So this is just the time complexity. Right. Oh, okay. Yeah. Well, the space complexity is because yeah. So the space complexity is because for this computation that we're doing right here, right? What is the space complexity? Well, we had to compute all of these the first set of LCS values, and that took linear space, right? And computing the second set of LCS values also takes linear space, right? And then you had to go find this J value, right? And yeah, so that doesn't take any additional space. Okay, so up to now we've only used linear space. Okay, and then after you find the J value, you need to do these recursive calls. Okay, but when you do the recursive calls, you can just reuse all the space that we have currently. We can reuse this linear space. Okay, so yeah, so altogether, since we're just repeatedly reusing this linear space, then in total the computation is going to take linear space. Okay. All right, so then the final part is to show that the time complexity doesn't increase when you do this algorithm. Okay, because now that we're making all these recursive calls, it might be that somehow the time complexity goes up. Okay. All right, so then we're trying to prove that the time complexity is still going to be quadratic like this. Okay, so we're just gonna we're gonna create this recurrence relation, and we're gonna solve the recurrence relation just by sort of guessing the right solution, which is this quadratic term over here, and then seeing that the guess is correct. Okay, all right. So now our recurrence relation for the time complexity is going to be like this. Okay, so T of mn is the amount of time to run this algorithm when these strings have lengths m and n. Right? So now this first part comes from the fact that you need to compute these two LCS tables over here. Okay, and this is going to take you quadratic time like this. Okay, so it's bounded by some constant c times mn. Okay. All right, and then you have these two recursive calls, right? Let's see. So yeah, okay. So you have these two. So q here is equal to what I call j on the last slide. So for some reason I can't write over here. Okay, right? Yeah. So whatever this j is, right? So you have one problem which is like this, and then you have one problem like this. Right? You have to find the paths in those. So that's going to take you this much time for each of these recursive calls. Okay. So now if you guess that the complexity is going to be no more than 2 times CMN. Okay, C is this constant over here. Then if you substitute this expression into this recurrence relation, we have that, so let's look over here. So we have that, this part is going to be no more than, q times n over 2 times 2 times c. Okay, and this other part is like this. And the final part is the CMN term. Okay, and then so you add everything together, and you see that this is still being bounded by 2 times CMN. Okay, so that so that we've shown inductively that this claim is correct. Okay, right. So again, all you need to do is you need to create this recurrence relation over here. You're going to guess that a solution is going to be like this, right, for some constant c. And then you just plug that into the recurrence relation, and you see that it works out. And so therefore, the complexity is linear. Okay, any questions about this? Let's see, what's this? What's the space complexity? We're showing p plus q. P plus q. Oh, well, so what you need to do in the previous step is you just need to store the final column of p and q. Okay, so you need to store you need to store all of these values. Let's see. Yeah, so p is this thing over here. Okay, so so they're just how many are there are m values over here. Okay, and likewise there are m values over here. So you just need to store these 2 times m values, okay? And that allows you to find this index j over here. Okay. Any other questions? Okay, so then that's all we have to say for this problem, for this dynamic programming problem, okay? So in fact, now we're going to move on to a new topic, okay? So we're going to move on from dynamic programming, and we're going to start a new part, a new topic, which is going to be network flows. Okay, so I'll see how much I can get through today, because All right. So anyways, so for network flows, so actually we're going to look at two problems. Okay. So we're going to start out by looking at this problem called maximum flow. Okay. And it turns out that this maximum flow problem is, oops. Right. I should be able to draw. Okay, right. So it turns out that this max flow problem is very related to another problem called minimum cut. Okay, so we're going to look at both problems together because each problem is going to help us solve the other problem. Okay, and each problem is actually interesting in itself. Okay, and in fact, this problem about max flow and min cut, this is a very important problem in computer science. Okay, it's widely used in combinatorial optimization because even though these two problems themselves, they're graph problems. Okay, but you can use these two problems to model many other kinds of problems, both on graphs and also in situations which do not look like they're graph problems. Okay, so you can map many other kinds of problems into a max flow min cut type problem. And then you can use this max flow algorithm to solve many of those other problems. Okay, so in fact here, they listed a bunch of these applications, and we're going to look at a few of them in the next lecture. Okay, so in this lecture, we're first of all going to to introduce this max flow and min cut problems, right? And then we're going to see how we're going to see some algorithms for solving these problems. And the next time we're going to see how to take some other problems and then transform them into max flow problems, and then use our algorithms to use our current algorithms to solve those problems. All right, and so one more thing I'll say about this is that the max flow and min cut problems are kind of they're dual to each other. Okay, basically meaning that each so in the max flow you're trying to find a flow which is as large as possible, right? You're trying to find a max flow, and in the min cut you're trying to find a cut which is as small as possible. Okay, and so it's going to turn out that these two values are like complementary to each other. Okay, so so it turns out that the max flow is always less or equal to the minimum cut. Okay, and so that's what we mean by duality here. All right. Oops. Why is this not? Okay, right. Okay, so let's first introduce the max flow problem. Okay, and then later we're going to talk about the min cut problem. Okay, so the flow problem is that it's a graph problem. So imagine that you have a graph, and then you have two special nodes. Okay, you've got a source node over here and a sink node over here. Okay, so S is the source and T is the sink. Okay. And now in this graph, you have a bunch of directed edges, and then each of these edges has a capacity. Okay, so each edge has this value C of E, which is called the capacity of the edge. Okay. And now what you're trying to do is you're trying to somehow like send stuff. Okay, so imagine that these edges are like actually pipes, okay, like physical pipes. Okay, and the capacity is like how much water can go through a pipe. Okay, like this pipe allows you to send like 10 gallons per second of water, right? And this pipe is smaller, so you can only send like 5 gallons. Okay, right. So we have these all of these pipes which make up this network, and now you're trying to send as much water as possible from the source S to the sink T. Okay, so that's the flow problem, right? And that's why it's called a flow, because you can imagine that this water is actually sort of flowing through the network from the source to the sink, right? And of course, we can try to use multiple pipes at the same time. Okay, so we can maybe try to use lots of these pipes at the same time. So yeah, so the reason this problem is challenging is because you don't know which of these pipes you should be using in order to send the maximum amount of flow from S to T. Okay, now when you do a flow, okay, so a flow just corresponds to like sending a certain amount of let's say water through each of these edges. Okay, so for example, here we're sending 4 units of water through the edge, right? And then here through this other edge we're sending 0 units, and then over here we're also sending 0 units. Okay, and then like over here there's 4 units of water, and so on. Okay. Okay, so this is a flow, and you see that this water is eventually going to arrive at this T location. All right, now the flow needs to satisfy some conditions. Okay, so these conditions are, 1 second. Okay, so these conditions are called the capacity condition and the conservation condition. Okay, so the capacity condition is saying that the amount of flow on each edge cannot exceed the capacity of the edge, right? Like here we said there's a pipe which only allows you to send 10 gallons, okay? And in this case, we're only trying to send 4 gallons, so that's fine. 4 is less than 10, okay? But on this pipe, you're not allowed to send any more than 10 gallons, okay? So this value here cannot be more than 10. Yeah, so F of E is denoting the amount of flow you put onto edge E, okay? And the amount of flow cannot exceed the capacity of the edge. Okay, now the next condition is called the conservation condition, okay? So the conservation condition is saying that, well, for example, if you look at this node over here, okay, you see that you have 4 units of flow going into this node, okay? And now, because the flow is going into this node, then it also has to come out somewhere, right? And for node 2, there are 3 different edges on which the flow can come out. Okay, you can either send the flow off to node 5, or to node 6, or to node 3. Okay, or you can even send it back to, or actually, no, let me not talk about that. Okay, yeah, so because 4 units are coming in, then the total amount that you send out from node 2 also has to be 4. Okay? Because, like if you think about water, right, if it goes into a node, then it has to come out of that node through one of the pipes out of that node. Okay, it can't get trapped. We don't allow the water to just stay in this node. Okay. All right, so therefore, if you look at all of the flow which comes into a node, this has to equal all of the flow going out. Going out from the node. Okay, so in this case, we have 4 units coming in, and then if you look at all of the outgoing flows, right, which are 4, 0, 0, right, we also have 4 units going out. Okay, and this has to be true for all of the nodes, right? Like over here, for example, or no, this one doesn't have any flow coming in. So over here, for example, right, we have 4 units of flow going in, and then the flow which goes out is either from in this direction or that direction, and you see that the total flow going out is also 4. Okay, now if you want to look at a more complicated flow, let's see, so this one, yeah, okay, so for example, let's look at this node over here. Okay, so this flow is a bit more complicated. So we see that the amount of flow going in, okay, so we have some flow from this direction, 4 flow, right? We have some flow here, which is 3, and then you have some flow over here, which is 1, right? So the total incoming flow, right, this part is going to be 8, and you see that the amount of flow going out is also 8. Okay, so again, the amount of incoming flow equals the amount of outgoing flow. And this is true for every node. Okay, this has to be satisfied for every node. Okay, so these are these 2 conditions which we have to satisfy for every node. Okay, now what is our objective for this problem? Okay, our objective is to send the maximum amount of flow possible from S to T. Okay, so therefore we're going to define the value of a flow as the amount of flow coming out of S. Okay, so for example, if we set the flow values this way, right? So all of these gray values are the actual flow values, right? And the black values are the capacities. Okay, so you can see that the flow values are always no more than the capacities. Okay, and now how much flow did we send from S? Well, we just add up the amount of flow on all the outgoing edges from S. Okay, so that is going to be equal to 10 plus 3 plus 11 is 24. Okay, so this flow sends 24 units of flow from S to T. And now we're trying to find a flow which maximizes the amount you can send from S to T. Okay, so maybe, for example, you can send 25 units or 26 units. Okay, right. Okay, any questions about the problem we're trying to solve? Okay, so yeah, so this is the max flow problem, okay? It's to find a flow from S to T with the maximum value, right? And again, the value is just you add up the amount of flow that you send from all of the outgoing edges of S. Okay, yeah, so in this case, right, we found a different flow, and the value of this flow is going to be 10 plus 4 plus 14, which is 28. Okay, so this is like a larger flow than the previous flow, and it turns out that for this graph, right, this 28 is actually the maximum flow. Okay, you can send at most 28 units of flow from S to T if you want to satisfy all of these capacity and conservation constraints.
正在上网课。
Okay. Any questions? Yeah. So if you don't have questions, please mute yourself. Okay. So now we're going to look at how to develop a max flow algorithm. Okay. All right. Now the simplest algorithm would be some sort of greedy algorithm. Okay. So for example, suppose you have a graph like this. Okay, and you're just trying to send flow from S to T. Well, a greedy algorithm would say that I'm going to look at all of the outgoing edges from S, okay? And whichever edge is the largest, has the largest capacity, right? So in this case, the 20 edge, right? I'm going to send as much flow on that edge as possible, okay? All right, actually, so, let's see. So maybe I should say it. Yeah, okay, so let me say this in a different way, okay? So a greedy algorithm would be that we're trying to send a flow from S to T, and the flow corresponds to some sort of path in the graph, right? Now, we're going to look at all of the edges on that path, okay? And some of the edges allow a lot of flow, like this edge 30 here, right? And some of them allow less flow, like these edges 20. So therefore, the amount of flow that you can actually send on the path is the smallest capacity of any edge on this path, right? Like here, for example, you can't try to send 30 units of flow, right? Even though this edge allows you to send 30 units of flow, this edge 20 here does not allow you to send 30 units of flow. Okay? So the maximum flow you can send is whatever is the minimum capacity on your path. That's how much flow you can send. Okay. So therefore, the algorithm, one greedy algorithm can be that we're going to try to find this path by always taking these edges with the maximum capacity. Oh, I'm sorry, I don't know why I keep zooming over here. All right. Okay, so initially we take this path, right? And then now we have a choice between the 10 edge and the 30 edge. So we're going to take the bigger edge, which is 30, right? And then we're going to take this edge. Okay. So this gives us this blue path over here. And now we have to find how much flow you can send on that blue path. And this is equal to the minimum of these capacities, which here is 20. And so this allows you to produce a flow with, I don't know how to, this is really, yeah, so this leads you to have a flow which is size 20. Right, because you can send 20 here, and then you can just send 20 units of flow along this path. Okay. All right, so that's one. Right, and once you send 20 units of flow, okay, you see that you can't run this algorithm anymore. You cannot send any additional flow anymore using this greedy algorithm. Okay, because for example, if you try to find another path from S to T, okay, so in this case, since we used up this entire path, right, this has a capacity of 20, and we're sending 20 flow along this edge, then we have to go for a different edge, right? Maybe we go for this edge, okay. But if you go for this edge, right, then once you get over here, you're stuck, right? Because now the only way to get to T is through this other edge over here, but this one has been completely used. Okay, so therefore you can't send any additional flow down this edge of 10. Okay. In other words, if you use the greedy algorithm, the maximum flow you can send in this case is 20. Okay. Now, on the other hand, let's say that we use a non-greedy algorithm. Okay, so non-greedy algorithm, what we can do is, let's say that somehow you found these two paths, the green path and the purple path. Okay, Now on the green path, we have to find the minimum capacity, right, which is a minimum of 20 and 10. So this means that on the green path, you can send at most 10 units of flow. Right? And on the red path, you can also only send 10 units of flow. Right? Yeah, so this leads us, so currently we have a flow value of 20, right? Because you're sending 10 on the upper path and you're sending 10 on the lower path. Okay. But now you can add one more path to this. Okay, you can add the blue path because there's still 10 leftover capacity on the on this top edge over here, right? Because you have capacity 20 and you're only sending 10. Okay, so you can send 10 additional units of flow on the top edge, right? And then once you get to this node, right, well, you can't make the flow go in this direction because this has already been completely used up. So instead, you're going to send the flow down over here. Okay. And yeah, so you're going to send the flow downwards. And once the flow gets, sorry, I have to, yeah, so you're going to send the flow downwards. You're going to send 10 units of flow like this. Okay. And then once the flow gets over here, right, you see that you still have 10 leftover capacity on this edge. So you can send the flow over here. Okay. So therefore, in total, what we've sent 30 units of flow. Okay, because you sent 10 units in the first on the green edge, you sent 10 on the blue edge, right? And then you sent 10 on the purple edge. Okay, so altogether you sent 30 units of flow. Okay, so this shows that the maximum flow is larger than 20. Right? The greedy algorithm only gets you 20 units of flow, but the maximum flow is going to be at least 30. Yeah, so in other words, the greedy algorithm is not going to produce the optimal answer in some cases. Okay, the greedy algorithm can only find you these sort of locally optimal solutions, and this is not equal to the actual maximum flow, the globally maximum flow. Okay, so all right, so I think we need to take a break over here, right? Because we usually have a break at like yeah, we have a break in the middle. So let's take a 5-minute break, okay? And then we'll come back at 11:05. Okay. Yeah, and if you have any questions, you can ask in the chat box. Okay, everyone, let's continue with the lecture. Sorry, drink some water. All right, so now we're gonna develop an algorithm to solve this max flow problem. So the first thing we need to do is define this concept called a residual graph. Okay, so the idea is that so all of these max flow algorithms are gonna work iteratively. Okay, meaning that they're gonna build up a flow over time. Okay, step by step. So let's say that you run this algorithm for a while and you have a flow. Okay, so let's say that you have this edge over here, which has a capacity of 17, and so far you've put a flow of 6 onto this edge. Okay, now maybe eventually, if you keep running the algorithm, you don't want to put a flow of 6 on this edge. You might either want to increase the flow or you want to decrease the flow. Okay. So we want to have some way of modeling either increasing the flow or decreasing the flow. Okay. So the way we're going to do that is we're going to take this current situation and transform it into this graph called the residual graph. Okay. So the residual graph, for each edge, you can make it into 2 edges. Okay. So if you have a positive flow on the edge currently, right? So you have a flow of 6. Okay. Then you're going to create 2 edges for the current edge. Okay. One in the forward direction and then one in the reverse direction. Okay. So the forward direction is going to say how much more flow can you put onto this edge. Okay. So currently we have a capacity of 17 and we've only put 6 flow onto this edge. So that means that you can put 11 more units of flow onto this edge. Okay, so going from U to V, we have a leftover capacity of 11 units. Okay, and also we made an edge from going from V to U, right? And this represents what if I want to decrease the flow on this edge? Okay, so for example, maybe I want to decrease the flow from 6 to 4. Okay. So in this case, I can think of decreasing the flow as sending flow back from V to U. Okay, but there's a limit to how much I can decrease the flow, right? Because currently I've sent 6 units of flow from U to V, so at most I can decrease the flow by 6. Okay, so that's why in the reverse edge from V to U, there's also a capacity, right, which is equal to the current amount of flow from U to V. Okay, so this is how we're going to build the residual graph. Right? We're going to look at our current graph and how much flow we're putting onto each edge. Okay, and then we're going to transform each directed edge into two directed edges. Okay, for one of them, right, we're going to put the residual capacity, and for the reverse edge, we're going to put the another residual capacity, which is equal to the current amount of flow. Okay, so this is how things are defined. Okay, yeah, and then the residual graph, which we're going to write as GF here. Okay, so this is going to be the residual graph based on the current flow F. Okay, it's just that we take all of the edges in our graph, right, and all of their flows, and then for each edge, we're going to do this transformation. Right, we're going to change it to two edges with these residual capacities. Okay. Now, one thing is that we're only going to do this for edges which have positive flow. Okay. So, for example, let me just erase this stuff. So, for example, if from U to V we currently have 0 amount of flow, okay, then our residual capacity from U to V is 17, right? And also going from V to U, we cannot send any flow, right? Because you're not sending anything from U to V, and so therefore you cannot decrease the flow anymore, right? Because you're sending 0 units of flow from U to V, so you cannot decrease that flow. So basically you would have an edge with capacity 0 over here, right? And in that case, we just eliminate this edge, right? We don't add the edge. Okay, so therefore we're only going to make these reverse edges when you have a forward edge with a positive flow. Right? If the forward edge has a flow of 0, we don't create the reverse edge. Okay. All right. Okay, so the next idea is this thing called an augmenting path. Okay. So the idea is that if you look at the residual graph, then Yes. So if you look at the residual graph, you see that there's some leftover capacity from U to V, right? So let's say let S is over here, right, and then T is over here, right? Oh, jeez. Yeah, and we're trying to send flow from S to T. Okay, so you see that there's some leftover capacity on this edge UV, which is on the path from S to T. So this is what we're going to call an augmenting path. Okay, we're going to have like this S node and this T node over here, and then you want to find some path in this entire graph from S to T, where if you look at all of the edges on this path, right, they have some positive leftover capacity. Okay, so maybe this edge has leftover capacity of 2, this one has 3, this guy has 4, and this guy has 2 and 5 and 6 or something. Okay, so now if you can find this path, then what you can do is you can add more flow from S to T. Okay, because on this path, we see that you can send at least 2 units of flow, right? You need to take the minimum of all of these numbers over here, and that's going to be 2. So you can send 2 more units of flow along this path. Okay, yeah, so, right. So we're gonna, so given a current flow, we're first of all going to compute this residual flow. Okay, and then you're going to find a path in this. You will try to find a path in this residual graph where all of these edges have positive capacities. Okay, and these edges can either be the forward edges, which are the edges in the original graph, right, or they can be these reverse edges, which are these edges that you add because these additional edges that we add. Okay, so the forward edges are the edges in the original graph, and the reverse edges are, if you look at the current flow, then anytime you have a positive flow along a forward edge, then we're also going to create a reverse edge. Okay, so in that graph, if you can find a path where, the minimum capacity is larger than 0, right? Then you can just send that minimum capacity along that path, and then you can increase your amount of flow from S to T. Okay, so that's why it's called an augmenting path, right? It increases your flow from S to T. Yeah, and then we know that, and then you can check that after you augment a path, right? Then F is still a flow, right? Because on each of these edges, we have this positive capacity. Okay, if the capacity is in the forward direction, then that means that, so let's go back to this example here. Yeah, if we're sending more flow over here, right? So let's say that you're trying to send like 4 units of additional flow. Okay, well that's fine because we have a capacity of 11 over here. Okay, and on the other hand, if we're using one of these reverse edges, right? If you're sending 4 units of flow over here, right? That is also okay, right? And what does it mean to send 4 units of flow on the reverse edge? It means that in the real flow, we actually decrease the flow by 4 units. Okay, right? Because this is going in the reverse direction. So after you send this flow, then then you decrease the flow on this edge by 4 units. Yeah. So the basic idea for any flow algorithm. Okay, so there are actually many max flow algorithms, but all of these max flow algorithms are based on finding different augmenting paths. Okay. The algorithms just have different ways of finding augmenting paths. Okay? But as long as you can find an augmenting path, then you can increase the flow. Right? So all of these flow algorithms basically just keep looking for augmenting paths and then increasing the flow until you cannot find any more augmenting paths. Okay? And at that point, you stop because you have a max flow. The only difference is how you find these augmenting paths. Okay, so so now we're gonna look at the first algorithm for max flow, which is called the Ford-Fulkerson algorithm. Okay, so the way this works is it's just exactly what I said. So you start with an initial flow, which is like 0 on all the edges, right? And then you just keep looking for augmenting paths. Okay, and as long as you can find an augmenting path, you can increase the flow. And eventually, if you cannot find any more augmenting paths, okay, if you get stuck because there are no more augmenting paths, right, then you return your flow. Okay, and then we'll prove later that when you get stuck, okay, when you cannot find any more augmenting paths, then the flow that you have is guaranteed to be the maximum possible flow. Right, we're going to prove that this is true. Okay, but let's first look at an example of Ford-Fulkerson. Okay, so suppose you have this graph. Okay, so these edges, they have all of these capacities. Right. So in the Ford-Fulkerson algorithm, we're trying to find an augmenting path from S to T. Okay, and to do that, you just need to find any path from S to T where all of the edges have positive capacity, positive residual capacity. Okay. So for example, so initially we have a flow of 0. Okay, so these zeros are denoting the initial flow. And in this graph, we just look for any path from S to T. Okay, so for example, this red path. All right. Now, how much flow can you send on the red path? Well, you need to you can only send the minimum residual capacity on this path. Okay, so that's going to be the minimum of 10, 8, and 10. So that's going to be 8. So we can send 8 units of flow on this path, right? So that's why we're going to change the flow along this path to 8. Okay. We don't change the flow anywhere else, right? Because we only have this one augmenting path right now. Okay, so that produces a flow of value 8. Okay, and also from this flow of value 8, we're going to create this residual graph. Okay. So remember, the way that we create this residual graph is that, so this is kind of confusing, the way they have these slides, because the animations are not synchronized. But anyways, remember that this 10 is the original capacity of the edge. Okay, and so because we're sending 8 units of flow along this path, right, then what happens is the residual capacity on this edge is going to be 2, right? 10 minus 8 is 2. Okay. And furthermore, we have this reverse edge, which has a capacity of 8, right? Because our current flow is 8, so at most we can send 8 units of flow back from node 2 to S. Okay, so that's how you build these two residual edges, and and then you just do that for and then for example for this edge. Okay, well this has a capacity of 8, right? And you're also sending 8 units of flow. So that means that you've completely used up this edge. Okay, so therefore there's no additional capacity going from 2 to 5. Okay, however, there is capacity going back from 5 to 2, right? And the capacity is 8. Right? You could send 8 units of flow back from 5 to 2. Okay, and then likewise over here, this edge from 5 to T, right? We form these two edges. Okay, yeah. So this graph, this GF over here, right? This is the residual graph resulting from this flow of 8. Okay, and now in this residual graph, we're going to find another path from S to T. Okay, so you see that there is another path from S to T, right? You can just take this red path, and you see that along this path, everything has positive capacity. Okay, and in fact, the minimum capacity is 2. So that means that you can send 2 units of flow along this red path. Okay, so now our total flow is going to be 8 plus 2. It's going to be 10 now. Okay, so so now we're going to have 10 units of flow. Okay, so in fact, this thing up here, this is the flow that you get after you send this additional 2 units. Okay, you see that you have, initially we sent 8 units of flow on this edge, but then after that we send 2 more units. Okay, so now you have a flow of 10 on this edge. Okay, and we also have a flow of 2 on this edge, 8 on this edge, and so on. Okay, yeah. So altogether, this is a flow of size 10 from S to T. Okay, now based on this new flow of size 10, we're again going to build the residual graph. Okay. Yeah. So so the residual graph, for example, this edge. Okay. What happened is that initially you could send flow from S to 2, right? But in our current flow, we've already sent 10 units of flow from S to 2. So that means that you cannot send additional flow from S to 2. Okay, so therefore you don't have a forward edge anymore, right? Because you've used up all of the forward capacity. Okay, you only have a reverse edge, and the capacity on the reverse edge here is going to be 10. Right? You see that you have a reverse edge from S to 2. Okay, and likewise, we build all of these other edges in this residual graph. Okay, and now in this residual graph, we're going to try to find another path from S to T. Okay, and you see that it's still possible to find another path from S to T. Right? We can take this red path over here. Okay, and how much flow can you send on the red path? Well, you take the minimum of all the capacities, which is the minimum of 10, 7, 6, and 10. So you can send 6 units of flow on this red path. Okay, so that means that now our flow increases from 10 to 16, right? Because we sent 6 additional units of flow on the path that we found. Okay. All right, and now based on this flow of 16, we're again going to construct this this residual graph. Okay, yeah, so this residual graph is actually based on the graph from the previous slide, right? Sorry, so let's call this G. So this actually has a flow of 16. Okay, so yeah, so let's call this guy G16. Okay, so this thing is the residual graph from this flow of size 16. Okay, and now from this residual graph, we again try to find a augmenting path. You see that there still is an augmenting path, right? And the minimum capacity on that path is 2. So therefore now we can increase our flow by 2 more units. So now we have a flow of size 18. Okay, and that flow is given over here. Okay, so this is our flow of size 18. Okay, I'm sorry that these values over here do not match the picture over here. Okay, so here you can see that we're actually sending 18 units of flow. Okay. Okay, and then from this flow of size 18, you again form the residual graph, right? You again try to you look for the minimum capacity. You find the residual graph. You look for an augmenting path. You find the minimum capacity, which is 1, right? And you send 1 more unit of flow. Okay, so that takes us to a flow of 19. Okay, and so now we are there any more? Oh, okay. Yeah, okay, so now from this flow of size 19, you form this residual graph. Okay, and now in this residual graph, we again want to find a path from S to T. Okay, but you see that, for example, you cannot go this way, right? Because here you only have a reverse edge. Okay, you don't have any edges from S to 2 anymore because you've basically, you've already sent 10 units of flow in this direction. So you can't send any more flow from S to 2. Okay, so therefore you cannot go along this this edge of size 10. Okay, but you can go over here. Okay, so we can try to send 1 unit of flow over here. But once you get over here, you see that all of the edges which come out from node 3, right? They don't have any more capacity. Okay, you see that there's only incoming edges into node 3. Okay, so once you send 1 unit of flow over here, you can't send that flow out anymore. Okay, and so this means that if you look in this graph, there actually is no path from S to T. Okay, you cannot find any path from S to T, right? Because you get, for example, over here, you just get stuck at node 3. Okay. And now, because you cannot find an augmenting path, then the Ford-Fulkerson algorithm terminates. Okay. And the claim is that when you terminate, right, we found a flow of size 19, and the claim is that this is the maximum flow in this graph. Okay? Yeah. Okay, so what is after that? Right. Okay, so so one thing that we can so we found a flow of size 19, right? Now, one thing that you can observe about this flow is that so the flow, let's see. Yeah, so if you start from this node S, right, then how far can you get? You can't go along this top edge, but you can go up to this edge of 3. Okay, so at most, if you do a graph traversal from S, you can get up to node 3. Okay, all right. So then we have this region consisting of node S and node 3. Now, if you look at how much capacity there is going out from this region, okay, you see that from node 3, you have one edge going out, which has a capacity of 9. Right? And then from S, you have one edge which, so we're going to divide the entire graph into 2 regions. Okay, one consisting of nodes S and 3, and the other region consisting of all of these other nodes. Okay, and because T is, so we're going to call this this thing over here A, and we're going to call this thing over here B. Okay, now you see that T is going to lie in the B part of this graph, okay? And S lies in the A part. And so therefore, you need to get flow over from the A part to the B part. Okay, and so that means that we need to look at edges which go from the A part to the B part. Right? So which are these edges? Okay, so you have an edge over here which goes from A to B. Right? And then you have another edge over here which goes from A to B. Sorry. You have another edge over here which goes from A to B. Okay. Now here, this edge, okay, we don't count this because it goes from A to A, right? Because S and 3 are both in part A of the graph. So we don't count this edge, okay? And then over here, we have an edge going from B to A, right? And we are also not going to count this edge because we're trying to send flow from A to B. So if you have an edge going from B to A, it doesn't help us send flow from A to B. Okay, so we're only going to look at edges which go from a node in A to a node in B, right? And so that's going to be these 2 edges. And now you see the total capacity on these edges is 19. Okay, and this is equal to our max flow. Okay, yeah. So the property that eventually we'll prove is that when the Ford-Fulkerson algorithm terminates, right, you have a maximum flow. And then from that maximum flow, you can find a cut whose capacity is equal to the maximum flow. Okay, so in our case, we can find a cut of size 19, and this has the same capacity as the max flow. Okay, so are there any questions about the Ford-Fulkerson algorithm? Right, so the entire algorithm is that. What does AB mean? Oh, okay. So so we defined A as you start from node S, right? And then you do, let's say, a breadth first traversal from S. And you see what are all of the nodes that you can reach from S. Okay, so you see that this is the gray region over here, right? Which has nodes S and 3. Okay, so that is how we define A. Okay, it's all of the reachable nodes from S. Okay, and then B is all of the other nodes which you cannot reach from S. Okay, so that's this B over here. Okay, right. And then the capacity, and then, well, I'll get to this, but yeah, and then you look for all of the edges which go from A to B. Okay, and the reason we care about those edges is because S is part of A and T is part of B. So in order to get flow from S to T, you need to take these edges which go from A to B. Okay. All right, so just to repeat the Ford-Fulkerson algorithm is that you have a flow, right? So let's say that currently you have a flow. You're going to find the residual graph based on that flow. You're going to look for an augmenting path in that residual graph. Okay, and if you can find an augmenting path, then you increase your flow. And if you cannot find an augmenting path, right? So let's just sort of go back to this algorithm. Okay, if you cannot find an augmenting path, then you return your current flow. Okay. All right. So so like one question is how do you find an augmenting path? Okay. Well, you can do this for example just using BFS. But isn't all the nodes in the graph reachable using BFS? No. So we are going to do a BFS on this residual graph, okay, on this residual graph GF over here. Okay, so you see that in this residual graph, for example, you cannot reach node 2, right, because you only have an edge from 2 to S. You do not have an edge from S to 2. Okay, you can reach node 3, right, but then you cannot reach node 5. So therefore, if you do a BFS starting from S, you can only reach node 3. Okay, so that's why A only has S and 3 in it. Okay, all right, now going back to how you find the these residual paths, augmenting paths, okay? What you do is you look in this residual graph, right? And then you do a, let's say a BFS or DFS or anything you want, okay? But what you're trying to do is to find some sort of path from S to T, right? You can either use a BFS for that or DFS or whatever you want, okay? But if there is a path from S to T, right, then you can find such a path, okay? And then on this path, you look for the minimum capacity on the path. And that's how much you can augment your flow by. Okay. And if you do a BFS or DFS and you cannot find a path to T, then that means that there is no augmenting path. Okay, so for example, in this final case over here, when you do a BFS starting from S, you cannot find a path to T. Okay, so there is no augmenting path, so the algorithm stops. Okay, any questions? If you use DFS, yeah, the algorithm also works, right? So you can use any pathfinding algorithm because all you're trying to do is go from S to T. Okay, as long as you can find a path using any algorithm, okay, then you can augment on that path. Okay, yeah, so I need to go a lot faster. I find it very hard to like lecture to to like my computer. So I'm sorry if this yeah. All right. So let's try to continue with this. So we just talked about max flows, right? And currently we have this Ford-Fulkerson algorithm, and I've claimed several times that it finds a maximum flow, right? But I haven't proven that to you. Okay. So the way that we can prove the Ford-Fulkerson algorithm actually finds a max flow is that we can relate the max flow to something else called the min cut. Okay. And then we're going to show this interesting duality property between max flow and min cut. And that is what allows us to prove that the Ford-Fulkerson algorithm achieves the max flow. Okay, so now I need to talk about this thing called min cut. Okay, so the idea, so the min cut idea, apparently there's some sort of, yeah, so I think somebody should mute themselves. Yeah, so apparently the history of this min cut problem goes back to like the Cold War. Okay, so what happened during the Cold War was so this graph represents like all of the railroads going out from Moscow, which is like over here. Okay, yeah, so apparently the U.S. didn't want the Soviet Union to like send stuff along their on their rail system, so they wanted to find like so these are all rail links. Okay, so they wanted to sort of disconnect Moscow from, let's say, this thing over here, which might be like Poland or something. Okay, so then how do you disconnect it, right? Well, you're gonna have to like destroy some of these railroad links. Okay, so they wanted to find like what is the smallest amount of railroad links that they can destroy in order to disconnect this this thing here, Moscow, from this let's call that Poland. Okay, yeah. And so, yeah, so this corresponds to like sort of destroying all the links along this, along this sort of cut over here, right? You see that if you destroy all of these links along the cut, right, then you completely cut off Moscow from Poland. Okay, and they wanted to find the smallest set of links to destroy. Okay, so you see that each of these links is associated with a number, which is, I don't know, maybe that's like the number of bombs you need to to like destroy that link or something. But anyways, they wanted to find a set of links such that the sum of all of these numbers is as small as possible. Okay, so that's why this problem is called min cut, because you cut the network into two pieces, and then this is like the minimum sum of capacities to cut it into two pieces. Okay, all right, so now, so let's define this more formally, okay? So let's say you have a graph. So again, you have a source node, which might be like Moscow over here, and you have a sink node, which let's say that's like, what's the capital of Poland? Warsaw, okay? So you're trying to go from Moscow to Warsaw, okay? Yeah, and now a cut is simply a partition of this entire set of nodes, right, into two parts, A and B. Okay, so for example here, right, we have this part A, which only has the single node S in it. Okay, and B is all of the other nodes. Okay, so this is a partition of the graph into two parts, A and B. Okay. And now this cut has a capacity. Okay, the capacity is the sum of all of the edges which go out from A into B. Okay, so for example, here you see this edge goes from A to B, right? So this entire thing here is B, right? So this entire thing here is B, right? And this edge goes out from A to B, and this goes from A to B. This goes from A to B, okay? So if you add up all of the capacities over here, right, which is 10 plus 5 plus 15, so this cut has a capacity of 30. Okay, now you can look at some other cut, right? So for example, you can set this thing over here to be A, and then you can set this stuff over here to be B. Okay, so in this case, if you look for all the edges going from A to B, right, that's going to be this edge, this edge, this edge, and this edge. Right. Notice that we don't include this edge over here because this goes from B to A. Right? You see that the direction of this edge is going from B to A. Okay? We only want the edges which go from A to B. Okay? Because ultimately you're trying to send flow from S to T, so you can only use these. So you know the thing that you want is for lots of edges to go from A to B. Okay? So therefore the capacity only includes the edges from A to B. And if you add up all of these capacities, you get a larger cut which has a capacity of 62. Okay, so for the ST cut, you can partition this set of vertices into any sets A and B. Okay, and then the capacity of that particular cut is going to be the sum of all of the edges going out from A. Okay, and now the minimum cut problem is that we want to find a cut which has the minimum capacity. Okay, so for example, the previous cut has a capacity of 62. Okay? But now if you look at this new cut, right, you see that the capacity is just going to be the sum of these black edges over here, right? Because these are the only edges which go from A to B. And they have a total capacity of 28. And it turns out that, out of all of the possible cuts in this graph, okay, the one that has the minimum capacity is this one, which has capacity 28. So the min ST cut problem is to find this minimum cut. Okay. Right. So now there's a relationship between flows and cuts. Okay, which is that suppose you take any ST cut. Okay, so ST cut means that it means that S has to be part of your A set. Okay, so for example, you cannot just define A to be like this set because this set doesn't include S. Okay. So your A set has to include S, right? And then T cannot be part of your A set. Okay, so T has to be part of B. Okay, so that's an ST cut, right? S is part of A and T is part of B. Okay. Now for any ST cut, if you look at the amount of flow across the cut, right, then that is equal to the amount of flow leaving S. Okay, so this is the flow value lemma. Okay, so for example, suppose you have a flow like this. Okay, so then the total flow total value of this flow is well, how much flow is going out from S? It's going to be 10 plus 3 plus 11, which is 24. Okay, and you see that in this cut, the edges that you have going out of the cut are these three edges, right? And then if you add all of the flow going out of A, subtract all of the flow going into A, you have that this is exactly equal to this value 24 here. Okay, as another example, if you set this to be your A, right? So the gray region is A here, right? So now how much flow is coming out of S? Okay, well, again, it's going to be the sum of 10, 3, and 11, so that's 24. Right? But now you have a different cut, and we're going to look at all of the flow going out from the cut, right? Minus the flow coming into the cut. Okay, so you have like, so how much is going out? It's 6 plus 0 plus 8 plus 11. Okay, so that, what is that? That is going to be 25. Okay, but you also have some flow which is going into the cut, right? Because you have some flow in this reverse direction. Okay, so you need to subtract the 1, and so altogether you get that the amount of flow across this cut, right, is equal to 24, and that is equal to the amount of flow going out from S, right? And the amount of flow going out from S is defined to be the value of the flow. Okay, so this flow value lemma again says that if you look at the value of the flow, and then you consider any cut, okay, any cut you want, then the amount of flow out of that cut minus the amount of flow into the cut is equal to the size of the cut. Okay, yeah, so one more example here, right? So again, you have like 24, the size of your flow is 24, and if you add up all of these numbers, right, and then you subtract the flow which is coming into A, then you get that this is equal to 24. Okay, so the flow value lemma works for any cut you want. Okay, so in terms of how to prove this, well, so the proof is actually pretty easy. So if you look, so what is the value of the flow, right? Well, it's defined to be the amount of flow going out from S. Okay, but now suppose, but now we claim that this thing over here is equal to this expression over here. Okay, where this is going to sum up over all of the nodes of A of the for each node V, which is in A. We're going to look at how much flow is going out of V minus how much flow is coming into V. Okay, and now the point is that all of these terms are equal to 0, right? Unless V equals S. Right? And the reason is that, remember, we have this flow conservation property, right, which said that if you have a node V, right, and if you look at all the flow going into this node, right, then that's equal to all of the flow going out from the node. Okay, and this expression is that's exactly what we have over here. Okay, we have that it's the amount of flow going out from V minus the amount of flow into V. Okay, and this is equal to 0 for every V unless V is equal to S. Okay, and we know that S is part of A, right? So that means that when you sum up over all of the nodes of A, all of these things over here are going to be 0, except for the term which is except for the V equals S term. Okay, and for the V equals S term, you get this thing over here, right? Because you don't have any flow going into S, you only have flow coming out of S. Okay. Right. Yeah, and then this expression, right? So this is if you sum up over all of the nodes of V, all the nodes of A of how much flow is going out from the node versus coming into the node, right? Then this is simply equal to the total amount of flow going out from A minus the total amount of flow coming into A, right? Because for each node in A, you look at how much flow goes out from that node minus how much flow comes into that node. And if you sum it up over all of A, you have the total amount of flow out of A minus the total amount of flow into A. Okay, and that's and this is equal to the and this is and this thing over here is equal to the capacity of the cut. Or sorry, not the capacity of the cut. It's the size of the flow out of the cut. Okay. Okay. So now once you have this property, then you have this weak duality property. Okay. So the weak duality says that if you look at any cut, right, and you look at the capacity of that cut, then the flow can be no more than the maximum flow cannot, or any flow cannot be more than that capacity. Okay, because what you have here is that you have that the amount of flow. Okay, so this is the amount of flow, right, and this is equal to the right. This is equal to the amount of flow going out from A minus the amount of flow coming into A. Okay. Right. Yeah. So right. So like to prove this property, which is that for any flow, right? This is for any flow and any cut. Okay. You have that the value of the flow is no more than the capacity of the cut. Okay. So we have this property, which is our lemma that we just proved. Okay. And so if you just subtract out this term, you have this thing over here, right? So this term is no more than the total amount of flow out of A, right? And you know that the total amount of flow out of A is no more than the capacity out of A, right? Because each of these F terms is less than the C term. Okay? And the total amount of capacity out of A is just equal to the capacity of A. Okay, so that means that the total flow, the size of this flow is no more than the capacity of this cut. And this holds for any flow and any cut. Okay, and so this means that, even the maximum flow, right, maximum flow, okay, this has to be less than the minimum cut, right? Because suppose the minimum cut is A over here, right? And let's say the maximum flow is F. Okay, well then you just plug F and A into this weak duality and you see that the size of this flow F is no more than the capacity of this minimum cut A. Okay, so the weak duality between flows and cuts is that the maximum flow is no more than the minimum cut. Okay, and that also means that suppose you can actually find a flow, okay, some flow which equals the minimum cut, okay, or sorry, you can find some flow which equals a cut, okay, so you somehow found a flow and you somehow found a cut and you find that their values are equal. Okay. Then this proves to you that your flow is as large as possible, right? Because whatever cut you found, so suppose you found that, let's just use this example. So here you found a flow of capacity, a flow of size 28, right? 10 plus 4 plus 14, right? So you have 28 coming out of S. And then if you look at the capacity of this cut, right? If you just add up the capacity over here, this is also 28, okay? So because the capacity is 28, then we know that any flow has to be less than size 28, right? Because, over here we said that for any flow, this is less than the capacity of any cut. Okay, so here you have a cut of capacity 28, and so that means that all flows are at most 28. And furthermore, you found a flow of size 28 over here, right? And so this means that your flow of size 28 is the largest possible, okay? Because we know that any flow is less than 28, and here you found a flow of size 28. So this is the optimum flow. Okay, so this is, we were talking about, if you find a flow, how can you possibly know that it's the largest flow? Okay, well, the way that you know is that you're gonna also look for another cut where the capacity of the cut equals the size of the flow. Okay. If you can find such a cut, then this proves to you that your flow is the largest possible. Okay, so that's why it's called a certificate of optimality, right? Because this cut over here certifies, right? It guarantees that your flow is maximum. Okay, any questions about this part? Okay, so now we're getting to the max flow min cut theorem, which when does this class end? Can somebody tell me when the class is supposed to end? Do I have like 5 more minutes, or do I have like at 55? Okay, so I have like 5 more minutes. Okay, all right. So I'll try to start this max flow min cut theorem. Okay. Yeah, so the so basically the point of this theorem is to show that the Ford-Fulkerson algorithm finds you the maximum flow. Okay, so we want to prove the Ford-Fulkerson algorithm is correct. Okay, and to do this, we're going to prove these two theorems. Okay, so the first one is the augmenting path theorem, which says that if you have a flow, right, and suppose there's no way to augment the flow, right, because from this flow you can derive this residual graph, and then you can try to look for an augmenting path in the residual graph. Okay, now if there is no augmenting path, okay, then the claim is that the flow has to be maximum. Okay, that's the first theorem. Okay, and the second theorem is the max flow min cut theorem, which is that the value of the max flow is equal to the value of the min cut. Okay, now the previous weak duality said that the max flow is less or equal to the min cut. Right, so the max flow cannot be more than the min cut. But it could be that the max flow is strictly smaller than the min cut, right? That could be the case. Okay. However, using this theorem over here, we have that no, the max flow cannot be smaller than the min cut. Okay, the max flow is in fact equal to the min cut. Okay, yeah, so that's what we're going to try to prove. And the way we're going to do this is that we're going to show these three conditions simultaneously. Okay, so the first condition is that suppose you have a cut AB, okay, and another flow F, and suppose the flow size of the flow equals the capacity of AB. Okay, all right, so that's the first condition. Second condition is that the flow F is a max flow. Okay, and the third condition is that there is no augmenting path starting from this flow. Okay, and now we're going to show that all three conditions are equivalent to each other. Okay, if you show that, then this means that so this means that if you have a so for example, to prove this one, right, what you need is to show that conditions 2 and 3 are equivalent. Okay, if you have a max flow, then if and only if you have no augmenting path. Okay, and then this second theorem over here is equivalent to showing that 1 and 2 are equivalent. Okay. Okay, so how are we going to show these three conditions are equivalent? Well, the first one is that suppose you have the first condition, then the claim is that F has to be a max flow. Okay, and the reason this is true is because we saw from the weak duality that the flow has to be less than or equal to the capacity. Okay, so therefore, if you have a flow which is actually equal to the capacity, then we said that this flow has to be maximum. Okay. All right. Now to show that 2 implies 3. So what we we're going to prove the contrapositive, meaning that we're going to show that if this is not true, if 3 is not true, right, then 2 is not true. Okay. And the reason is that if 3 is not true, then there is an augmenting path. Okay. But if there is an augmenting path, then that means that you can send more flow along that path. And so that means that F is not a max flow. Okay, right? So if F is a max flow, then there cannot be any more augmenting paths. Okay, and the final part is to show that the third condition implies the first condition, right? Meaning that if there is no augmenting path, right, then the amount of flow is equal to the capacity of some cut. Okay. Now, initially we don't know which cut that is, right? But I'll tell you how to find. But I'll tell you that if you have a max flow, I'll tell you how to find a cut which has a capacity equal to the flow. Okay. Yeah. So So suppose you have this flow F, which does not have any augmenting paths. Okay. So and now let's let A be the set of vertices that you can reach from S in the residual graph. Okay, so you have some flow, right? And the flow leads to some residual graph. Oops, sorry. Okay, the flow leads to some residual graph. Okay. And now you're going to take the node S, and let's say you do a BFS in that residual graph. in order to find all of the vertices that you can reach in that residual graph. Okay? All right. Now, by definition, you can reach S itself. And then you let A be the set of reachable vertices. Okay. So S is, of course, part of A. Okay. And furthermore, T is not in A. Okay. And the reason is you do not have an augmenting path. Okay. So therefore, if T was part of A, then that means that T is reachable from S. But if T is reachable from S, then you have an augmenting path in the residual graph. Okay, so if you do not have an augmenting path in the residual graph, you cannot reach T. So therefore, T is not in A. Okay, so now we're going to form this cut, which is going to be A is going to be all the nodes you can reach from S, and then B is going to be all of the other nodes. And we know that T is going to be part of B because you cannot reach T. Okay. Okay, so I guess I'm out of time over here. Okay, so I think I guess I need to stop at this point because I'm not done with this proof yet. It's probably going to take another 5 minutes. So I guess I'll stop at this point and then we'll continue on Thursday. Okay, yeah. And so, so guys, I know that it's kind of hard for me to lecture, over the internet. So I'm sorry if things are not that clear. If you have any questions, just please ask me. You can come to my office. You can send me email. You can ask on Piazza or something. Okay, right. And then, okay. And then, so I guess I'll see you guys on Thursday. Again, it's going to be online. Okay, through this WeChat program. Okay. All right, so that's the end of the lecture. If you have any questions, you can keep asking in the chat box. Okay. All right. So somebody's asking about weak duality. So weak duality is just saying that. Let me erase all this stuff. Okay. So weak duality is saying that you can take any flow, okay, and then you can take any cut. Okay. Now the claim is that the flow is no more than the capacity of the cut. Okay. And why is that? Okay, well, so we can go sort of through this proof again. So the reason is that, we know the flow is equal to the amount of, so the size of this flow, which is the size of the flow going out from S, okay, this is equal to how much flow goes out of A minus how much flow comes into A, right? This was the previous lemma that we had, okay, the flow value lemma, okay? Right, and now now if you just remove the second term over here, right, you're left with how much flow goes out from A, but this cannot be more than the capacity going out from A, right? And that by definition is the capacity of this cut. Okay, yeah. So therefore, the flow is no more than the capacity of the cut. Okay. Now, why is this weak duality useful? It's because you can use it to certify, to prove that a flow is maximum. Okay, because you know that because suppose you find some cut, okay, and it has some capacity, let's say 28. Okay, and now if you can find another flow which also has size 28, okay, then you know that this is the best possible flow, the largest possible flow, right? Because by weak duality, the flow has to be less than the capacity of any cut, including the size 28 cut. Okay, and now since here you found a flow of size 28, right, then this means your flow is as large as possible. Okay, so the weak duality is useful because it can be used to certify that a flow is maximum. Okay, and then we have a strong duality, which is that, in fact, not only is the flow less than or equal to the min cut, the max flow, right? The max flow is in fact equal to the min cut. Okay, not just less than or equal to, but it's actually equal to. Okay, and then that's what I was trying to prove, which I'll finish up next time. Okay, any other questions? Okay, so yeah, if there are no other questions, then I'm gonna log off, and yeah, again, you guys can send more questions through through something else.